Welcome to the next session, my dear friends. In the previous session, we are discussing the sludge digestion tank in volume reduction. So in volume reduction, we are discussing the procedure how to calculate the volume reduction with reduction in the moisture content. So here, so for m mass, okay, if the mass of the solid is m, so the mass of the sludge produced at moisture content of P1, mass of sludge produced at moisture content P1 is equal to 100 by 100 minus P1 into the mass of the dry solids, okay. So this is what we have learned. Now what is the volume of this? So this is the mass of the sludge produced when m is the mass of the dry solids. So this is the mass of the sludge we are producing. So what is the volume of the sludge? At moisture content P1? Volume of sludge produced at moisture content P1 is equal to, this is the mass by density of the sludge, so 100 by 100 minus P1 into mass of dry solids by rho of sludge, okay. So this is nothing but the volume of the sludge V1. Let us take this as V1. So this is the volume of the sludge at P1 moisture content, okay. Now here volume of the sludge produced at moisture content P2, okay. So similarly volume of the and mass also we can write at P2, okay. So mass will become 100 minus 100 by 100 minus P2 into m is the mass at moisture content P2, okay. So volume of a sludge produced at moisture content P2 is V2, which is equal to 100 by 100 minus P2 into m. This is mass by density of the sludge, again by density of sludge. So this is V2, this is V1, okay. This is V2 and this is V1. So mass of the solids, generally whatever be the moisture content, so you are reducing the water content, you are not reducing the solids content. Are you getting me what I am saying? Whenever we are doing sludge thickening, we are reducing the moisture. So the solids mass, this solids mass is m. This m will remain same in both the cases. So what is the m value for the first case? What is the m value for the second case? So m is equal to P1, this is not P1, this is mass, okay. So that is, sorry, volume V1, this is V1 into rho of sludge into 100 minus P1 by 100. V1 into 100 minus P1 into rho of sludge 1. So let us take this is rho of sludge 1 and let us take this rho of sludge 2 because water is varying, okay. Rho of sludge 1 and rho of sludge 2, which is equal to V2 into rho of sludge 2 100 minus P2 by 100, okay. So this is the relationship we got. Now, so here 100 we can cancel. If we assume that rho of sludge 1 is nearly equal to rho of sludge 2, if rho of sludge 1 is nearly equal to rho of sludge 2, then we can cancel them also. So we will get a relationship that is equal to V1 into 100 minus P1 is equal to V2 into 100 minus P2. So this relationship is very, very important in sludge digestion. So when you are reducing the moisture, when we are reducing the moisture content, that is P, so what is the reduction in the volume? What is the reduction in the volume of the sludge? That you will understand from this relationship. For example, I will tell you, I will take this relationship, I will use this, I will explain you how much moisture that it will, how much volume it will lose when we reduce the moisture. What is the importance of this moisture reduction? Why it is that important? We will understand it with a simple example. Let us assume that the moisture moisture content is, okay, so 98, okay, 98. I have reduced it to moisture content that is 96, so I have reduced it by 2%. I have reduced it by 2%. So V1 into 100 minus P1, that is 2, is equal to V2 into 100 minus P2, that is 4. 100 minus 96, that is 4. So then V2 is equal to V1 by 2. 2 by 4 it will come here, V1 by 2. That means the volume is reduced by 50%. V2 is equal to V1 by 2. Simply I have reduced the moisture just 2%. The volume of the sludge has reduced it by 50%. So how much volume of the sludge digester we can save? 50% means half of the initial value. So that is why this is, so simply 2% of moisture extraction will lead to a volumetric compression of 50%. So that is why the importance is there for the sludge thickening in order to save the volume of the sludge digester. Unnecessarily, if you send V1 volume, so which is containing lot of water, so it does not of any use. Okay. So likewise, generally we thicken the sludge. Okay. We thicken the sludge, and by this means we reduce the volume of the sludge. Now, next is strength reduction. Strength reduction. See here, strength reduction means BOD is destruction. Okay. So whatever the sludge you send into the system, whatever the sludge you send into the system, that sludge will convert some part into gases, some part into a liquid, some part into a digested sludge. Okay. I already told you here there will be two phases. First phase is acid fermentation stage. Okay. The first stage is acid fermentation stage, where acid formers. So in this stage, acid formers will act on the sludge and they form acids and alcohols. Okay. And in the second stage, methane formers. Methane fermentation. So here methane formers will come and act on the sewage, the sludge. They convert the sludge into the methane gas and also CO2, H2S, but majorly 70% of the gas is methane only. Okay. Now here sludge digester, if you look at the sludge digester, so it will be looks like this schematic diagram of drawing. So this is the inlet and this is the portion . So there will be a dome on this top, so floating dome. because to safely send out the gases out of the system, so we need a dome like this. So from here, because the important thing is methane gas, so we will collect the gases which are coming out of this sludge digester from this vent, okay, and we send the sludge from this inlet zone. This is the location where we send the raw sludge, and this raw sludge will be categorized. See, whenever we send the raw sludge will be present here, and during the decomposition the raw sludge will become the old sludge. So that is fresh sludge, digesting sludge and digested sludge, like that. So we will pour the fresh sludge here, the fresh sludge. Now whenever it has got digesting, it will come down, because we are removing, at the same time we are removing the digested sludge from here. So we remove the digested sludge from here. So this is digested sludge. This is digesting sludge. So this is solid out. So this is solid and this is gas. So there will be another vent here to take care of the supernatant liquor. So whatever the after digestion, during the digestion, some amount of this sludge will convert into gas, solid, and so there will be a gelatinous, filamentous material, liquid material that will come onto the top, that is called supernatant liquor. So that supernatant liquor, generally it contains lot of BOD. So that supernatant liquor we will take again into the system. I told you already, whenever the BOD is more, so territory treatment is needed. So the territory treatment we give for the supernatant liquor. Okay. So we will take out the supernatant liquor from here and we will send that back into the system, because its BOD will be in a range of 3000 ppm, which is very, very high. So so likewise, whatever the raw sludge volume you take, so after digestion its volume will become 1/3. So almost it loses 70% of the volume. Okay, it will be having only 1/3 percentage of volume, 33% of volume it will be having after the digestion. So during this process, so how much gas it is producing, how much gases it is producing is a very, very important concept, because I told you again and again the same thing. Methane gas is a very important gas which is having the calorific value. So we need to understand how much gas is being generated per kg destruction of the organic solids. Okay, for kg destruction of organic solids. So here there is an equation for understanding that. So the gas production. So the gas production. So during the sludge digestion, the gas will be produced in at volume of 0.9 meter cube. Okay, 0.9 meter cube per kg volatile solids. Okay, per kg volatile, because non-volatile means they are like inorganic solids. So those inorganic solids does not contribute for the gas production. So the organic solids which are volatile, which can be degraded, so they can only contribute for the production of methane gas or any gas. It may be methane, it may be CO2, or it may be H2S, anything. Okay, so majorly 70% is methane, very, very important. Okay, so now here for kg volatile solids destructed. per kg volatile solids destructed. So in that 0.9 meter cube, so there will be 70 percentage, okay, 70 percentage will be methane, 70 percentage will be methane. After this methane, CO2 will take the second place, that is 20 to 30 percentage of 20 to 30 percentage of CO2, and remaining gases, whatever the gases H2S and other gases, they will be very less, they will be traces, okay, H2S and all, so they will be traces. So now here we are looking only about the calorific value. CO2 will not have any calorific value, but H2S, CH4 will have. So what is the calorific value? So the calorific value of CH4, the calorific value of CH4 is 5200 to 5800 kilocalorie per meter cube. 5200 to 5800 kilocalorie energy it can give per meter cube of production. Okay. So here questions will come like this. Questions will come like this. So first of all, how many solids are present? Okay. So they will tell you these many solids. See, if you look at the question, they will be here doing the question is difficult. Doing the question is difficult. But how to do is very easy. How to do, that means if you look at this system, so the solids, from where the solids are coming into this system, you need to think very deeply while doing the sludge digestion problems, because here the gas, I have simply asked what is the energy that you can get from this destruction of the solids. I will tell, and I will tell, so solids, from solids destruction the gas is generating, from solids destruction gas is generating. So from where solids are coming, the solids will come from the first stage, primary sedimentation tank to secondary sedimentation tank. From every location the solids will come here. So they will tell, so in the influent these many solids are there. So the efficiency of primary sedimentation tank of solid removal is this much. Secondary sedimentation tank solid removal is this much. So in that solids, volatile solids percentage is this much. Because here from the volatile solids only the CH4 is coming. So from every component, primary sedimentation tank and secondary sedimentation tank, how many solids are being removed from there, those solids will come here. Okay, so we need to calculate how many solids are being removed there, so that the solids which are coming here we will understand. And in that solids, what is the proportion of volatile? What is the proportion of volatile we need to find. So proportion of volatile, after finding the proportion of volatile, so these volatiles are being destructed again if they give the efficiency of the sludge digester. So these many volatiles are coming into it, but in the sludge digester these many volatiles are destructing. So that means in that 100% volatile solids, only 70-80% are being destructed in the sludge digestion tank. Then we need to again calculate how many volatile solids are being destructed, and from that volatile solids destructed 0.9 meter cube gas is coming. But that 0.9 is also not only for methane, that is for methane, carbon dioxide and other gases also. Now in that 0.9, 0.7%, that means 0.7 into 0.9, that is 63.63 meter cube is of methane. That is the methane production. Again he is not asking methane production, he is asking methane calorific value. Again this is the methane calorific value per meter cube. So this much of, that means when he is asking simply what is the energy that is being evolved from methane, if he is asked that simple question, we need to do this much of lengthy calculation. So that is why these kind of questions are even important in engineering services also, and also GATE. Okay. So design of, so this is all about the strength reduction part. So strength reduction part is this. Now the design, let us go into the design of the sludge digester. design of see design of sludge digestion tank. If you look at the sludge digestion tank figure there, so every day on daily basis fresh sludge will come into the tank, digested sludge we will remove out of the tank. So this is a regular process. So what sort of equilibrium is present in between these two? If it is linear, okay, if it is linear, then in that manner we will design the sludge digestion tank. If it is not linear, if it is parabolic, okay, generally it may be linear or it may be parabolic. Linear means there will be some relationship between these two. So if you look at the graph, let us take the fresh sludge on x-axis and digested sludge on y-axis. Okay, so if the fresh sludge incoming fresh sludge and digested sludge outgoing, okay, so both are linearly varying somewhere like this. So if the fresh sludge is coming more, then the digested sludge is removing also more. Linear means what? They should be proportional. So this may be one variation. Here sometimes what happens? The fresh sludge may be coming less, but the digested sludge may be moving more. Okay, so this kind of graph, or it may be like this also. So similarly different kinds of graphs may be coming. So generally it may be linear or it may be second degree curve, that is parabola, square parabola or parabola simply. So now that is why if it is linear we use one kind of formula. If it is not linear, then we use another kind of formula. First of all, let us see what is the formula which we use if it is linear. If the volume change is assumed to take place linearly, okay, if the volume change is taking place linearly, then volume of the sludge digestion tank is equal to Vf plus Vd by 2, Vf plus Vd by 2 into T. Vf plus Vd by 2 into T. So what is Vf? Volume of fresh sludge. Volume of fresh sludge added per day, and Vd is volume of digested sludge removed per day. Volume of digested sludge removed per day. That is Vd. So T is the digestion period. T is digestion period. So this digestion period varies with the type of microorganism present. Okay, this digestion period varies with the type of microorganism present in it. Generally, if it is mesophilic microorganisms, generally they are mesophilic, which will work in a temperature range of 20 to 40 degrees, Generally, they take a time of 15 to 20 days. 30 to 60 days. And Next one is thermophilic. Thermophilic work in a range of 40 to 60. Thermophilic. It takes in a range of 15 to 20 days. Depending upon the type of bacteria, so type of the microorganism, the value will change. Okay. So when the temperature is more, digestion period will be less. This is when there is a linear relationship between the fresh sludge and the digested sludge. Fresh sludge and the digested sludge. When they are not linearly related, okay, when they are non-linearly changing, if they are taking a non-linear path, then the volume of the sludge digestion tank so Vf minus 2 by 3 into Vf minus Vd into T. So this is the volume of the sludge digestion tank when the change in between the fresh sludge and the digested sludge, the relationship between the fresh sludge and digested sludge is like this. And again here if you consider, okay, sometimes we also allow the what do you say, this kind of the flood water like storm water. Okay, so during the flooding seasons it is not possible to withdraw the digested sludge because the sludge drying bed will be flooded. So that is why the storage is needed to be kept inside the digestion tank during the monsoon period. So if you consider the monsoon period also, okay, if we assume that the sludge cannot be disposed, digested sludge, that the digested sludge cannot be disposed during monsoon period, because whatever the digested sludge we will simply bring out of the digestion tank and we will just spread it on the land. That is called land irrigation. We will discuss that in the chapter called disposal of effluents. So whatever everywhere we are seeing the effluent, okay, we have seeing here second degree treatment only. After every second degree treatment we are getting the effluent, either it in the form of a liquid or it in the form of a solid. If the BOD is more, then we will send it back into the system anyways. So if it is fit for disposing, then only we call it as disposal. So now those effluents, how to dispose them, how to manage the disposal, we will discuss in the coming topic. That is the next step of taking care of the sewage. So here we are also what we are doing, this digested sludge disposal is needed. Where do we dispose? Whatever the gases that are coming during the digestion, that will be trapped. Whatever the supernatant liquor that is coming, that will be sent back into the system because its BOD in a range of 3000 ppm. So the digested sludge is safe to dispose. This needs to be disposed onto the land, but during flooding season those lands will be completely wet, so that cannot be disposed. That should be disposed in a dry state. So that is why in that period of time we cannot take out the digested sludge. So if you consider that also, then you need to create some volume for that period also. Okay, in that case the volume will be Vf minus 2 by 3 Vf minus Vd into T plus digested sludge during the monsoon period. So this is T is monsoon period. This T is similarly the same case in the linear also. In the linear also it will become, if it is linear, then it will become Vf plus Vd by 2 into T plus Vd into capital T. This is for linear variation, this is for parabolic variation. Okay. So likewise, generally we design the sludge digestion tank. So this is all about the sludge digestion tank. This is all about the sludge digestion tank. So we are now discussing the next topic, that is septic tank. We are now discussing the next topic, that is septic tank. So what is meant by septic tank? Septic tank, you might have, everybody might have seen the septic tank, and everybody uses, in every household there will be septic tank. So let us discuss what is septic tank and all. Septic tank is a combination of both sedimentation tank and sludge digestion tank. If you combine both the sludge digestion tank and sedimentation tank, it means if you look at the septic tank, everybody might have seen the septic tank. So whatever the sewage, sludge that will enter into the septic tank along with the water. So whatever the flush system we use, it will take the sludge. Whatever the sludge we are disposing, that will be taken into the septic tank with the help of the water. That is nothing but flush system. So now inside the septic tank, the solid sludge will go, as well as the water which is carrying it will go. As we all know, water does not need any treatment, it can come out safely. But the sludge, whatever the sludge we are disposing, that needs treatment. So separation of the sludge and water needs to be taken place inside the septic tank. So that role can be taken care by the sedimentation part, settling zone inside the septic tank. When the settling is over, so the sludge is settled deep into the septic tank. So there it will undergo anaerobic digestion, because so there won't be any free oxygen available there in the septic tank. It is completely closed. That is why the decomposition, whatever that happens, will happen in anaerobic mode. So if you look at the septic tank also, we will be having a trap which traps the gases. There will be a long pipe, if you see in your homes also. So that is gas out. Okay, so whatever the liquid part, so once the sludge is settled down, so if you look at the septic tank, so this is the influent. So there will be a pipe to trap the gases, a long pipe will be there to trap the gases and all, and this is the settling zone. Somewhere up to this is the settling zone. So because we will be constructing a baffle like kind of arrangement, because if you don't construct this wall, the sewage whichever is entering will directly go into the outlet without moving through this settling chamber. So in order to divert it into the settling chamber, we need obstruction like this. Then so whatever the sewage that is coming, the sludge will enter into the settling zone and go. So this is settling zone. Here this is sludge zone. This is sludge zone. Okay. So this is a common schematic view. I am just taking a schematic view, nothing much. So Now here the sludge, we need to remove it after some time, 1 year or 2 years or 3 years of time. We generally remove this using some kind of pumping equipment. So the sludge cannot be go out upon its own gravity like kind of thing. We need to take out the sludge by using some kind of pumping equipments. So this is how the septic tank will work. Okay, the working mechanism of septic tank, whenever we release any kind of solids along with the water, it will go into the septic tank, it will hit the obstruction, go down and enter the settling zone. Here the sludge will fall down into the sludge zone and the water, clear water, will go out. Sometimes this water also carries some kind of BOD. So that is why this water, whatever the effluent that is coming out of the settling tank, we will send that effluent onto the soak pit or dispersion trenches kind of thing. Soak pit and dispersion trench is nothing but a small pit in which this effluent will go and percolate into the ground. So we will cover this small pit with some kind of brickbats and all, so that dispersion will take place. So those kind of mechanisms, so the effluent will not directly go into the drains, it will be land irrigated using soak pits and dispersion trenches. So now likewise we work. So that is the complete process flow, complete process of the septic tank, complete process of the septic tank. Generally these septic tanks can also be used for villages where there is no proper drainage is available. So we see the septic tank for households only, but the septic tanks can also be taken as a municipal drainage collection source also, because when there are villages where there is no proper drainage facilities available, so if the village is having a capacity of 200 persons odd, then for those 200 persons, if no proper drainage is available, then we can construct a big septic tank so that we can collect. In that condition, the septic tank will also collect the sullage. So domestic waste also, wastewater also we need to collect. Here if we are using it in household, the sullage will enter into the drain, only the human excreta will enter into the septic tank. But whereas if it is constructed for a village kind of thing, for common people, then sullage will come into it. Okay, in that cases what happens, the effluent may contain some BOD, more BOD, which cannot be easily discharged into the local rivers and all, local drains and all. So that is in those cases when the BOD of the effluent is also considerable, which is coming out of this septic tank, then in that case we will send that effluent onto soak pit or drain, dispersion trenches or cesspools, leaching cesspools. All these kind of mechanisms are available in order to take care of the effluent. So likewise we do. So septic tank can be used for household activities. Also the septic tank may be used for the group of community, group of people presenting in a community. So depending upon the drainage availability in that locality. So now here this is how the septic tank will work. Okay. Now how to design the septic tank? What are the design parameters of the septic tank? How to design the septic tank? Let us see. So design parameters. Design parameters. The flow of sewage, okay, the flow of sewage will be around 40 to 70 LPCD, 40 to 70 LPCD. So this is the flow of sewage into the septic tank, and sullage. So without sullage, this is the flow of sewage. Without sullage, so with sullage it should be 90 to 150 LPCD. 90 to 150 LPCD if we are considering sullage also, this is 90 to 150 LPCD. Rate of accumulation of sludge. So how much sludge will accumulate per day? Rate of accumulation of sludge. Rate of accumulation of sludge is 30 liter per capita. 30 liter per capita per year. 30 liter per capita per year. So that is the sludge production. So 30 to 40 approximately, it is 30 to 40 liter per capita per year. Detention time. (12 to 36 hours). Detention time is 12 to 36 hours. And length to width ratio. It is approximately equal to 2 to 3. And the width should not be less than 0.75 meter. Width should not be less than 0.75 meter. Minimum liquid capacity, that is 1000 liter. Minimum liquid, that means the water holding capacity. Minimum liquid holding capacity is 1000 liter. Depth 1.2 to 1.6 or 1.8. Depth will be around 1.2 to 1.8 meter. Cleaning period. Detention time is different. Cleaning period is different. Cleaning period. Generally it varies with the size of the tank. It varies from 6 months to 3 years also. 6 months to 3 years also. Anywhere it will rise because it depends upon the size of the tank and the how many users are using that tank. Okay. Cleaning period may vary depending upon the size and the number of users using that septic tank. Freeboard we use 0.3 meter. So here this is freeboard. So these are the design parameters. These are the design parameters of the septic tank. So in the next session we will discuss how to design. In the next session we will discuss how to design the septic tank and what is meant by Imhoff tank. And after that we will discuss the oxidation ponds. That's it. So these are the different treatment units we are having as far as gate is concerned. Okay. So after completion of that we will complete the treatment of sewage questions, and then after that disposal, how to dispose the effluents which are coming out of these secondary treatment, we will discuss that. And after that only 2 topics, solid waste management and air pollution, noise pollution. So by that we will complete the syllabus. Okay. Thank you so much.